Okay, I think we're going to get started here. Hopefully people are seeing the title slide here. Welcome to the whole building lifecycle assessment for the B3 guidelines. This is a training program for the B3 program, and I'll be presenting today. My name is Rolf Jacobson. I'm a research fellow here at the CSBR. Also joining us is Liz Kutschke. I work with her and Pat Smith on the B3 program and SB 2030 program here at the CSBR. So a few logistics real quick. This is kind of a webinar format, so you all will be muted. At least for most of the show. And if you do have questions, please just let me know through the chat, and Liz will keep her eye on that too. I'll try and answer that as they come up, or answer those as they come up. Hopefully there's also going to be some time at the end for a Q&A period. So this session is being recorded as well. So if you have a need to go back and review parts of it, you can go to our training page within a week or so. It'll be uploaded there. You can view it for free. For architects here, if you need AIA credit, please drop your AIA number into the chat, and we will be saving the chat at the end and recording that. We'll be back in touch with you about those credits. It is AIA credits are available for this session. So let's see. Yep. So Liz dropped a link to the training and education page. That's where this will show up. I think I'm going to skip over the learning objectives for now. This is a look at today's agenda. So we're going to start off with a very kind of basic and brief overview of LCA. What it is, and then talk about some whole building LCA tools. Those are software tools that architects and engineers and designers can use to do an LCA on their building. We're going to talk about which one of those tools are currently allowable within the B3 program, specifically for LCA Guideline M.1A. We'll dive into those requirements there later on, and then talk about how to kind of achieve compliance. We'll run through a couple examples and look at the kind of optimal workflow to achieve the targeted reductions there. So for those of you that are sticking around for Thursday, we're going to switch gears from a webinar format into more of a class or exercise-based format. It will be a regular Zoom meeting, and so everyone will be able to talk. Please have the Athena Impact Estimator loaded on your laptop or something before you come, because we'll be working through some exercises. I'm going to do a run through of the program, and then we'll kind of break into small groups or work independently on some exercises. So moving into the overview of LCA, I'm going to try and switch screens to a different presentation real quick. So this is a presentation that actually anyone can download from the Athena Institute. We have permission to use it today. They put together a very nice background kind of slideshow on LCA. So I'm going to run through that quick. It's about 10-15 slides long. At its most basic, LCA is kind of an inventory of the flows between a product and nature. And then the second piece of that, after you've categorized them and listed them and quantified them, is translating that into an environmental impact or environmental impacts. And if you take a typical kind of life cycle here, starting with extraction and processing of the raw materials in the upper left and working through all these different phases to the lower right, where finally you've got the building or the product built and it's used, it's being repaired. Finally, it's being disposed of. At each one of those life cycle stages, obviously there's resource inputs and waste or emissions. And that can go to either land or water or air. And the first part of that assessment is just keeping track of what those resources, maybe that's energy inputs, raw material inputs, or water, and also tracking the waste that's coming out. So even if we kind of wrap that one-way life cycle into a circle through building reuse or recycling or something like that, we still are going to have this process of resources in and emissions out. So the inventory part is really, keeping track of those, and a life cycle analysis is going to start on that basis, and they're going to track really basic inputs like water, iron, sand, energy, that kind of thing, and then they're going to track the emissions that are coming out and the impacts that are coming out. And oftentimes that's taking the form of specific chemicals that are released into the land or air or water. And so that's the inventory part. And then we have the assessment part where they take that inventory and try and estimate the potential for environmental degradation from each of those. And there's, of course, many different parts of the environment that can be degraded with these activities. So, maybe we're concerned about depletion of the ozone layer or eutrophication of our water. Climate change is, of course, a big one. So we're trying to keep track of those impacts in all these different categories to really get a broad sense of its impact on the overall environment. The value of LCA. So number one, it's going to provide some real data rather than what people sometimes call greenwashing. It provides that data in hopefully a transparent way. Charts, EPDs, we'll take a look at in just a moment, that are provided by manufacturers, so we can compare different products or materials to each other. We're also given an opportunity to look at what we call embodied impacts. And I think historically in the building profession, we've all focused much more heavily on operational impacts, such as operational energy or water consumption of a building. And this LCA gives us a chance to take a step back and consider what the embodied impacts are, and even dive down into what they call hotspots or parts of the building enclosure, specific assemblies and materials that may be having a greater impact than others. Gives us the opportunity to identify those and change if we find a way to find another product. So just walking through each one of those in a little bit more detail. On the real data side, we're often confronted with these things called proxy measures. I'm sure we're all very familiar with that because we're bombarded with these as consumers all the time. Recycled content is a proxy measure. The claim for a local product is another good example. And really, we don't know what the environmental benefits of those claims often are. Sometimes recycling, it consumes more energy or more materials than generating a new product or material from scratch. So LCA helps us kind of get to behind those claims a little bit and find out, what the real numbers are. And hopefully we can find something like this. This is an environmental product declaration where there's performance data listed. So we can see how much and what waste is produced, how much energy is used in the creation of this product. And that's going to be quite a bit more useful if we're interested in attacking this from kind of a scientific standpoint. And hopefully, more and more product manufacturers are providing these EPDs. The B3 program does require EPDs, a certain number of them under a different guideline. It's Guideline M.1B. This presentation is focused on M.1A, which is the whole building life cycle analysis. But just to let you know, M.1B is where the EPDs are kind of collected. So there is a place for those as well. Okay, so the embodied impacts, of course, we're interested in what the building materials and building processes are adding to the energy of the building. We can make claims like net zero, but often those are made in terms of energy, just looking at the operational side. And we need to take a step back and consider the embodied impacts too, because actually it turns out many times they are quite substantial. So this is a little graph showing, even after 60 years of building life, those embodied impacts in blue are still a significant component of the overall energy consumption. So one advantage of considering them upfront is that doing something to reduce the embodied energy has an impact really on day one. You don't have to wait around 60 years for those benefits to accrue. So that has some meaning given the urgency of the climate situation. So the hotspots are where the largest building impacts are happening. And if we do an LCA model, we can use that model, the information that it generates, to really dive down a little bit deeper and see where those large impacts are coming from. And let's say we're interested in tracking the greenhouse gas emissions, or the GWP, embodied carbon, or the embodied energy of our building. And using a graph like this, we can see that there's really the walls are contributing more than their fair share to those. So we can drill down into those deeper and use the LCA model results to figure out where those impacts are coming from. And in this case, it looks like glass is the largest single contributor. So we could then make a decision, well, maybe if we're trying to meet an embodied carbon target or reduce the embodied energy, maybe we consider reducing the window to wall area ratio or reducing the glass somehow. Perhaps looking at a different insulation product or something like that. We can use the LCA to optimize those kind of choices and have kind of the biggest bang for the buck. There are some limitations, of course, with LCA. It's not a silver bullet. It only addresses some of the environmental impacts that we're concerned about. So especially if we're interested in kind of responsible resource extraction, that's going to be much better handled through additional certification programs like SFI or FSC. LCA analysis struggles to get down to that level of detail. It also struggles in terms of human health and indoor air quality. So maybe if we're very focused on those, we want to use a different, we want to use something additional like a well building standard or something, because that's going to do a better job of addressing human health than just a simple LCA analysis. The other important thing to keep in mind is that LCA is not an exact science, it's an estimating science. So the answers that it gives aren't very precise. But even if they're not precise, we can still use them to help inform what they call here direction. Even given a pretty large margin of error, it's often still easy to see that we want to move, try and move away from concrete towards wood, that kind of thing. We can make those kind of choices given this data still relatively easily. Okay. I am now going to switch back to my PowerPoint. And talk about this a little bit more in detail. So again, LCA is going to be more useful in determining relative impacts rather than absolute values. And you see here a little chart showing how they try and deal with this. There's a lot of uncertainty in LCA. As I said, it's an estimating science. So you can see the kind of range of uncertainty. It's this particular product category in green, and they've got kind of error bars on the top and the bottom, and it's quite a wide spread, right? It goes from like 0.45 all the way up to 17. So that's a huge range. And even for this specific product shown in the lighter blue on the right side, there's still quite a big range there. Uncertainty, that's plus or minus 20%, I think, shown up there. So it's not, we can't use, we need to be very careful about using LCA, the absolute values coming from this software. Why do the impacts vary so much? Well, the answer is LCA is quite complicated. So as you can, I'm sure you can imagine trying to go through each one of these life stages and figuring out what the scope of the raw material inputs and the emissions are at each one of those phases is quite daunting. And confusing, you know, the question is repeatedly, how far do you want to expand that circle? How far do you want to dig back? And there is a standard that's been developed to kind of help guide this process. But even with this standard, you know, the standards are often quite broad and general. So although they do provide some help, there's still going to be a lot of leeway built into each kind of LCA analysis as to what actually gets included and what doesn't. But it does help to set some of the scopes and boundaries for this analysis. The Tracy 2 methodology, which was developed by the EPA, is a really important methodology because it's adopted by most of these software, whole building LCA software, and it's really what is doing the translating behind the scenes between the LCI, the inventory, or the list of resources and emissions, and how those get calculated or transferred to environmental impacts. So again, the LCI is kind of the list of specific chemicals or molecules or resources that are used. And then the life cycle analysis is layered on top of that, where we transpose those into actual environmental impacts. And we calculate those, or we estimate those environmental impacts using something called indicator molecules. And I'm sure that most of us are familiar with some of those indicator molecules already. For example, CO2 is frequently used as an indicator for global warming. Ozone is frequently used for smog or ozone depletion. The reason why we use those chemicals or indicator molecules, I should say, you can imagine if we're trying to compare the impacts of, let's say, an elevator door to a piece of drywall. The production and use of those products is going to be result in vastly different collections of emissions, chemical emissions, and resources. So we have to have a common basis for measuring those, and that's what we use the indicator molecule for. Taken together, all of these indicators are supposed to represent a more or less comprehensive view of the impact on the environment. So you see a bunch of them listed here, everything from global warming down to smog and ozone. Primary energy is typically listed as well. So again, the benefit of using the indicators is going to allow for comparison of two products or materials that might be quite different, might have quite a different LCI or list of emissions. But they are just that. They are indicating potential effects. It's really hard, of course, to definitively track the emissions of a certain chemical back to, you know, so somebody got cancer because of this particular chemical that was emitted as this piece of drywall was made. Of course, that's quite difficult. So they remain indicators. In terms of going back to the stages of a building here, LCA, this is something that was developed under these protocols here. They've named all these different phases. So, excuse me, the A1 through 3 phase is really the product stage, where we're talking about the creation, the manufacturing of the building materials. And then phases 4 through 5 is the construction of the building. Phase B is the use phase of the building. It can include impacts from maintenance or repair, even replacement of the different components of the building. And phase C is the end of life stage. So you can see listed there deconstruction or demolition, the impacts from that, transporting that waste and processing it, and finally disposal. There's an additional phase called phase D, which is, quote unquote, benefits and loads beyond the system boundary. That the best example I can give of that is the carbon sequestration benefit that's often given to wood. Phase D is kind of a still questionable phase at this point in LCA science. So most of the time we do not include phase D. Most whole building LCA software is going to give you the option to include phase D impacts or not. And for the B3 guidelines, at least, we do not want those included in the results. You'll also see that operational energy and operational water use are included in the use stage, phase B. For the B3 program, again, we're looking at tracking those in other guidelines, obviously. So we don't include those in the LCA analysis. All right, lastly, there's a note here on building lifespan. And obviously building lifespan can make a very large difference on your LCA results, because you can have a product such as vinyl cladding, which looks maybe pretty good, low energy compared to other claddings like brick or metal on day one, but vinyl doesn't last very long. So if you set your building lifespan at 100 years, there's going to be maybe 2, 3, maybe even 4 replacements of that vinyl cladding over that 100-year time span. And each time those are replaced, we're adding more impacts. So by the end of 100 years, the impact from the vinyl choice of vinyl cladding could actually be more than the impacts from brick or metal cladding, which have a lifespan of closer to 100 years, but they're not replaced. If we selected a building lifespan that was very short, 20 years, then it would be biased towards those shorter life products. And we don't really know how long our buildings, are going to last. A lot of times we're building with very durable materials, concrete and steel, commercial construction that's torn down in 20 or 30 years. And on the flip side, we're building residential buildings out of wood, which maybe you can consider those shorter lifespan materials, except that they're maintained and seem to stick around often for a lot longer. So we have to have a consistent standard. For the B3 program, we have aligned ourselves with LEED, and LEED selected early on 60 years as kind of a consistent lifespan for the building when we're doing LCA analysis. So that's what we use in all the LCA models that you will be producing. Just set that building lifespan at 60 years, no matter what building, the construction materials or building types that we're modeling. Okay. Check the chat here. We do have some breaks coming up. Hopefully 2 breaks. We'll see how the timing goes. I think there's a break coming up. I'm going to keep plowing ahead right now, though. Transitioning to the whole building LCA tools. This is a little chart. These are not all whole building LCA tools, I should say. At the top, we have SEMAPro and GABI, which are really for use by LCA specialists to perform kind of a bottom-up LCA analysis. And so you're going to need a specialist to do an analysis using SEMAPro and GABI. For consumers, architects, designers, we're really looking at the lower 2 boxes. B is an eco concept and EC3. EC3 is a relatively new one. Those 3 are kind of middle of the road. They're really more focused on specific products than whole buildings, although it would be feasible, it'd be possible perhaps to build up a whole building analysis using those, but it would be kind of time consuming and difficult because you're adding 1 product at a time. The software in the lower box is really designed for whole building analysis. So there we have ready-made assemblies, or we have BIM import capability where we're importing the entire building design into the software. And we can get the results from the whole building much more quickly. And those are right now primarily Tally, one-click LCA, EC3, and Athena Impact Estimator. So whole building LCA is trying again to quantify the embodied environmental impacts through all those different life phases, life stages, phases of the building, from the material and the raw material extraction and the creation of the products and the building materials all the way through the demolition of the building. Typically, the whole building LCA is going to look at the structure in the enclosure, including foundation and interior floors. Sometimes that may include interior walls and finishes. Typically, a whole building LCA is not going to include fixtures, furnishings, and the building equipment. So that'll include plumbing and HVAC equipment, furniture and lighting, and that kind of things are all removed from an LCA analysis. And as we saw earlier, sometimes the operational impacts, energy and water use are included, not for the B3 program though. So this first one here, Athena Impact Estimator, it's kind of like the original, at least in North America. It was developed by Athena Institute. It's not very graphical. It's more of a tree-based structure, as you see in this little screenshot. There's, you click, you add different assemblies as you go. There's a lot of pre-made assemblies, and you can enter the square footage of those in the little pop-up windows, and it's fairly easy to use. The material impacts are taken from an NREL database, along with some proprietary information that was developed by Morrison Hershfield. So it's a little bit of a mix and match type of a database that's been kind of, I wouldn't say cobbled together, but put together over time to get as many building products and systems in there as possible. And it's pretty comprehensive at this point. The pros are that it's really easy to use and navigate. You can see just in the screenshot how kind of simple it is. You can generate basic building models really quickly early on in the design. You don't need to have a very well-developed building design to use this. So that's going to allow for comparisons really early on in the design process when they're still most valuable. The engineers can be changing structure systems, or the building design can be modified to and see the results to see if there's can be some savings before things get too far down the road. And again, I think one of the benefits is that the database, although it's a little bit put together from various resources, it is based on North American industry. So the results are a little bit more applicable than some of the other software. The cons are, as you see here, one of the cons, this is a graph from Athena. The graphs are not very presentation ready. Frequently, we will just take the raw data out and make our own Excel charts. There's no visual confirmation of the model building. You're not working with a BIM model or anything like that. You only have this tree structure to operate in. You can double check stuff using the bill of materials, but there is no visual confirmation that you've got the complete building modeled. Again, the database is a kind of a mix of public and proprietary information. And sometimes, especially with the proprietary stuff, those data sources aren't always well documented. One other nice thing here, I didn't list, oh yeah, I did, yeah, it's free. So a lot of people it's kind of an easy bar for entry. If you're just starting out, you don't need to spend thousands of dollars on a whole building LCA software. Okay, Tally is kind of the next one that came to the forefront here in North America. It was developed by Kieran Timberlake. Originally, it uses Revit building model for takeoffs. And that eases some of the modeling, because a lot of the work in Athena is, of course, trying to calculate square footages and things like that. You've got to do those takeoffs yourself. If you've got a building model, Tally is really handy, because you can import that from a BIM software, Revit, for example, into Tally, and you've got all those takeoffs already there for you. The material impacts are taken from something called the GABI database and then customized for the North American market. The GABI database is originally a European industry database. So they've tried to adopt that a bit for the North American market. I don't know if anyone knows exactly how good that translation has been. But we'll talk more about how to use these tools in a bit to make sure that the results are meaningful. The pros of Tally, one of the pros, it generates some very nice looking graphs and reports. And it's got a very extensive database of the materials. It's easy to use if you're already familiar with Revit. And like I said, it's going to really significantly ease the takeoffs process and can speed the LCA modeling. There will also be coming soon a bill of materials import to EC3. So EC3 we'll talk more about in a few minutes. It's a little bit different than the other software types because it's built around an EPD database. And so that can be handy in some ways we'll discuss in a little bit. Okay, some cons of Tally. One of those major ones is, of course, the Revit model may not be ready. It may not be complete as early in the design phase as you'd like to be doing an LCA analysis. You've kind of got to wait till you've got a building built in Revit before you can use it. And in some cases, you're already gonna be a bit far down the design path, and certain things are gonna be locked in, and opportunities for embodied carbon savings are already gonna be lost. So you've got to be aware of that. Another thing is the Revit model may not include all the components that are required in a whole building LCA. And on the flip side, it may include some that aren't required. So you'll have to do some careful picking and choosing of which ones are to be taken out and maybe which ones need to still be added. Okay, one-click LCA is similar in concept to Tally. It works best with a BIM import. There's a lot more variety of different imports available. My understanding, I have not used one-click LCA very much at all. So this is the one I'm least familiar with. But you can see here, there's quite a number of different imports. You can even import from some energy modeling software such as IES to give you kind of the building geometry and takeoff information. So that can be nice. It was originally primarily used in Europe, but it's growing pretty quickly here in North America. They've managed to integrate their database with North American EPDs. One benefit of integrating actually with energy software is you can run some life cycle cost analysis as well as LCA. So that's kind of an innovative feature of one-click. As I said, some of the pros, integrates with a large variety of other software. It's going to ease the LCA modeling because you're getting takeoffs from those other pieces of software. There's a view here on the right of some of the reporting capabilities. So that looks pretty good in terms of visuals. It's pretty clear reports. You don't need to export to Excel and make your own charts if you don't want to. They also have an add-on tool called Carbon Designer, which I have not tested myself, but it seems like it'd have the potential to address this concern with, not really having an BIM model early enough in the design process. So you can start with Carbon Designer, even with a rough concept of your building, just basic building info like floor area, number of floors, and it's going to generate a reference building. And you can start playing around with that reference building to see what strategies make sense to reduce embodied carbon and that kind of thing early on. Okay, on the con side, EPDs are sometimes a bit dangerous to use for an LCA database because EPDs are coming from a wide variety of different manufacturers, and some of them may be using different scopes for their products and materials. And so the consistency can suffer a little bit on databases that are built from those. Again, some of the similar drawbacks to Tally, the software models like Revit and IES, they may not include all of the components required to do the full building LCA. Some materials in addition, some materials might need to be removed. So you've got to track all of that before you can run off with the results. And finally, it is, again, an expensive software, more similar to Tally. We've looked back in the B3 program and taken a look at see which of these tools project teams are using. So about half are using Athena at this point. About 1/3 are using one-click. About 1/5 are using Tally. Okay. I'm going to just stop real quick again and check the chat. If there's any questions, yeah, again, feel free to just type them in the chat. EC3 is kind of the new kid on the block. It was developed in the last few years by the Carbon Leadership Forum. And it's kind of an interesting tool. Essentially, it's an EPD database. That's basically what it is. And they've developed some things around this EPD database, some tools. And they're free. So like Athena, you can log in, you can sign up and log in, use EC3 for free. They have a tool called the Plan and Compare Buildings tool, where you can do a whole building embodied carbon analysis. It really is restricted. EC3 is a carbon leadership forum tool, so it really is restricted to carbon, embodied carbon. You're not going to be able to find embodied impacts in terms of any of those other environmental indicators we were talking about, like ozone depletion or water eutrophication or anything. It's restricted to embodied carbon. They have a second tool called Plan and Compare Materials, where you can look at within a specific material category, you can compare different materials to each other. You can even pull up specific products because it's this EPD database. So you can go and find perhaps the product that you intend to use in your building and find the EPD and compare it to others within that product or material category and see if you've got one that has, you know, the low kind of impact you're looking for. On the plan and compare building side, this is a chart of a building, like an example building that was developed. This tool with an EC3 works the best with the BIM import. And to deal with some of the uncertainty, it's going to provide a couple kind of benchmarks or references for your building. You see here on this chart 3 different colors. One is what they call a Carbon Leadership Forum baseline. That's the purple. The green is showing what they think is achievable, kind of the best performance in class. And the gold is the realized or the building as designed. And so you can see across this spectrum of different building components how your building is stacking up against the baseline and what's achievable. You can use the tool early on before you have specified specific products by using generic product category EPDs. So you don't have to wait around till all the materials are exactly specified. On the con side, it does have some pretty big drawbacks. Since the tool is based on this EPD database, it does not include the construction impacts, the maintenance impacts, or the demolition impacts. Those are the phases A3 through 5 plus B and C. So it's really focused on the product, the embodied carbon of the product as delivered to your job site. I've also found that the data entry in this tool is really clunky. You can't enter materials by the typical takeoff quantities like volume or length. You have to translate them oftentimes into weight. I think I said volume. You've got to translate them from length of surface area into weight and volume. And so that's a pain in the butt. It makes entering this a whole building by hand rather difficult. So if you're going to use this, you'd have to probably do it from a BIM import. The other unfortunate drawback at this point for EC3 is some product categories have very few EPD entries. So it's not going to provide very accurate estimates for those product categories. And examples are like cladding and roofing. So if you have a product category such as roofing with or cladding with only 3 different EPDs in it, of course, you're not going to get a very good picture of what the broader spectrum of impacts are in that category. And it's going to be pretty hard to find your specific cladding. So because we don't have all the phases built into this particular software, we cannot use EC3 for B3 whole building LCA. It will be probably valuable to you in other ways though, specifically using the Plan and Compare Materials tool. For certain product categories, there is an abundance of EPDs available, so you can go in and find, you know, which type of drywall you intend to procure, which type of foam sheathing, that kind of thing, and there will be different manufacturers and products available, and you can try and find ones that perform better than the ones you've specified, or make sure that the one you're specifying is falling, you know, in the lower range. And you can generate like graphs. We've looked at this before. You can kind of compare your product to where the industry average is. So we found it to be a bit more helpful on this side of the tool, and it will become more helpful over time as hopefully more EPDs are added. This is really a functionality that the other whole building LCA tools don't have at this point. They're really more generic. They don't have the link to the EPD database. On the con side, again, as I mentioned, many of the product categories have pretty low numbers of EPDs. One unfortunate example is the structural steel. There's only 13 in all of the USA at this time. So, you know, ideally, you'd be able to dive into this tool and pick out some steel from a certain manufacturer and then record that in your whole building analysis as savings. But that's probably not going to be likely until more EPDs are loaded into this. Okay, welcome back, everybody. There was one question that came in during break asking about ComCheck software. And I am not that familiar with ComCheck. My experience with it has been as kind of a commercial energy code compliance tool. So I'm not sure that it relates all that well to Athena, but I may not be aware of all that's really included in ComCheck these days. That was quite a while ago. So if others have any thoughts about that, you know, feel free to write something in the chat. Or Liz, maybe you have some comments, but I can't really add too much to that. Let's see, I'm going to go back to my PowerPoint here. Okay, so we're going to go into the guideline requirements for the M1A guideline here. Looking at the intent, the guideline requirements themselves, and then a longer section on how to achieve the compliance. Yeah, thanks for dropping that link, Liz. All right, so the goal obviously is to reduce the embodied global warming potential of the building, of the whole building. And it is focused, M1A is focused entirely on global warming potential. There were earlier versions of B3 that asked for reductions in multiple different environmental categories, and we kind of abandoned that approach, or we did abandon that approach several years ago. So now we're focused entirely on achieving reductions in embodied carbon. There's three major paths to choose from. There's a whole build, what we call the whole building LCA approach, an assembly level LCA approach, which is based on kind of structural bays, and finally a material level LCA approach, which is based on a calculator that we developed. No matter which of those three paths you choose, there is an additional requirement to submit a whole building LCA model at the end, just representing the final design case. If you happen to have a B3 small project, which is under 20,000 square feet, then that whole building LCA model is not required at the end. But if you don't fall into the small projects category, no matter which of these approaches you select, you will have to produce at least one whole building LCA model. So how do these work here? At the product and material level, this path 3, it's kind of a simplified approach. The calculator is just a little Excel tab. It's very easy to use. And you're just simply using drop-down menus and selecting materials that are lower impact, perhaps than the ones that you've specified first. It is limited though, and we'll talk about those limitations in more detail a little bit. You can only compare materials that are functionally equivalent. So for example, OSB and plywood sheathing, you can select which one you want to use for the product or for your project. it wouldn't be fair, for example, to compare closed cell spray foam with fiberglass bats though. And this gets back to that term of functional equivalence, because fiberglass bats don't provide all the functions that closed cell spray foam provides. So if you were going to compare these two, you'd have to add, you know, an air barrier, a vapor retarder for the fiberglass bat to get the same functional performance as a closed cell spray foam. So maybe you want to do the assembly, you'd have to add in those additional sheet goods or spray on air barrier or something, whatever you intend to use before you can really compare those results. And that isn't going to be possible using this simple of a calculator. At the assembly level, you could do that kind of comparison. This is easier to do than a whole building model because you're just looking at kind of a slice through it. But again, you have to make sure that that slice is functionally equivalent. So if there's a roof that's providing R48 and you want to compare that with a building design that's doing R20 and making up for that with more insulation somewhere else, you can't do that very well using this assembly level calculator. To do that kind of analysis, you really got to step up to the whole building level. And that's going to be more time intensive, of course, but it allows you the greatest flexibility, the greatest number of options when you're trying to reduce or drive down that embodied carbon. For example, it's going to allow you to even change the building shape and the surface area. And those are some major opportunities, of course, to reduce the embodied carbon of a building, but you can't do those with path 2 or path 3. So of the recent B3 projects, this is a pie chart showing what paths are being used. Most people are selecting to use the whole building LCA modeling path. Very few are doing the assembly level LCA path. Quite a number, though, are still using the material calculator. And that is, that's kind of the path, the default path actually for small projects, just because it's such a less time intensive. So for the guideline requirements themselves, path 1, this is the whole building LCA approach. The requirement is to document at least a 10% reduction in whole building global warming potential. And that's, of course, relative to something. So we have to set what we call a reference building. And there's different ways to create a reference building. It's documented quite well in the LEED the LEED manuals. You can have a kind of a baseline building based on your standard building approach. You can try and find an existing building. There's a number of different ways to do this. You might be able to use a software that provides a reference building for you, for example, with EC3. I take that back, you can't use EC3, but perhaps one-click LCA would be a good option using the Carbon Designer approach. With path 2, you're also asked to document a 10% reduction in GW embodied global warming potential. Again, we have to have a reference case to compare that with. And that reference case would, again, it might represent your standard envelope, your standard collection of envelope assemblies, the roof and the wall and the foundation systems that you're comparing to your design, your low GWP case. For path 3, the requirement is to use this little calculator tool. It's called the B3 LCA Material Selection Calculator. And it gives you a score depending on the different material types you select from the drop-down menus. And for most B3 projects, you've got to get a score less than 1.65. If you have a B3 small buildings project, we are really trying to help those small buildings use this path. So we've increased that target or that requirement a little bit to up to 1.75. So if you fall below that and you've got a project that's a B3 small building, you can pass. One significant limitation of this approach is you have to have a building that utilizes kind of one dominant structural and enclosure type. It says here you have to have, that has to make up at least 60% of the building's structural volume and exterior surface area respectively. If you've got a building that's, maybe 3 different parts and each one is using a different structural system or a different type of cladding, and there's no particular structure cladding that makes up more than 60%, then this is a path that you can't use. Also, you've got to have assemblies and materials that are represented in the material selection calculator itself. So it's not going to be exhaustive. In fact, it's quite limited, and especially in some categories. So you may be limited by that as well. Okay, so how to achieve compliance with the whole building, with the path 1, the whole building LCA approach. As I mentioned before, the software types that are allowable at this time are Tally, Athena, Impact Estimator, and one-click LCA. So EC3 is not allowable at this time. Again, we are setting the building service life at 60 years. We want the assessment scope to cover everything A through C. That's called cradle to grave, and omit phase D, which is the beyond building life. When you're comparing the reference building and the selected design, they have to be functionally equivalent. So what that means is they've got to both meet all the owner's project requirements. They have to have the same function and basically the same floor area. These things don't have to be perfect, but they should be relatively close. We don't want to compare a 20,000 square foot building to a 40,000 square foot one, for example. And they have to meet the minimum energy performance and other performance requirements of the B3 and SB 2030 programs. So to include, what to include in this model. As we talked about earlier, this is kind of review. We're going to be including all the structural elements, the posts, the beams, and the bearing walls. We want to look at all the foundation, the basement, the roof, all the intermediate floors. We want to look at the exterior enclosure, everything from the outside, the cladding, all the way to the inside, including the interior finish. We want to include the glass, the glazing in the building. Also parking structures, even unattached parking structures, parking ramps on the site need to be added to the whole building LCA. So what to omit? The non-load bearing interior walls and assemblies can be omitted. There's the interior finishes, except the interior finishes that are part of that exterior wall assembly. Those can all be omitted. As I mentioned earlier, the furnishings and equipment can be omitted, electrical and mechanical equipment. Everything on the site can be generally excluded, including landscaping and parking lots, with the exception of the parking ramps. So there's generally, this path follows the LEED life cycle impact reduction credits. But in this case, there's a 10% impact reduction required for GWP only. In addition, LEED options 1, 2, and 3, which are really focused on building and material reuse, are not going to be considered for compliance in our program, at least when it comes to meeting M1A. And finally, I think there is a difference still between the LEED whole building LCA models and ours, in that we do not want to see the interior partition walls in our LCA models, and I think LEED will allow those. Sometimes it's just more work to include those, unless you've got a BIM model, and then hopefully it's easy to strip those out. So again, the whole building path, path 1 is going to open up the broadest array, the largest number of different options to reduce the embodied carbon. All these different options, with the exception of changing the building service life and the building floor size, are available to you. So you can change the building shape, which may impact the surface area. You can change this building structural spacing, which is the grid layout. You can do assembly substitutions and design changes. You can change the thicknesses of materials, different layers. You can change the window to wall area ratio. And of course, you can work all the way down to the simplest, most basic thing, just swapping out one material for another. So really all those, there's quite a wide range of opportunity, which is the good thing about this path one. Here's a few, I think I did threw in two examples of using this path. I'm gonna walk really quickly through these, but this is a look at the Itasca Biological Station, which was a wood frame building, super insulated, as it turns out. And it's a single story slab on grade building. We did some LCA modeling for this building and just use it as kind of a test case to see whether 10% is achievable or not. This is an interior picture of it. It's kind of a classroom-based building or lab-based building. There's a base case that's shown on the left, the total embodied carbon, and then a kind of a reduction case or the design case. And in this chart, it's broken down between the impacts of foundations versus walls versus the structure versus the roof. So you see those represented in different colors there. This is a list I'm not going to go through in great detail, but just showing what changed. You're going to have to track this from model to model, so you're going to need some type of system to keep track of these changes as you're trying to achieve a savings. You can see at the bottom, we achieved 20.8% savings on embodied carbon for this case. And the majority of those savings came from the strategy, the dematerialization strategy, where we just reduced the thickness of the concrete slab a little bit from 5 inches down to 4 inches. And we used some material substitutions. So we did notice that there was some very high GWP materials used. There was a bitumen membrane on the roof, and there was closed cell spray foam used in the walls. So we tried swapping those out for some lower GWP, functionally equivalent materials. So the spray foam was exchanged with cellulose plus an air and vapor barrier, and the peel and stick roofing membrane was replaced with 2 layers of roofing felt. And those changes alone were enough to achieve that 20.8% savings. So as you go through these, you'll begin to develop a feel for which materials are really high GWP and which aren't. And you can use that to your advantage as you do more and more LCA models. This is another example case, Wells Fargo office building. This is more of a commercial style, obviously, 6-story concrete frame. The base case was a site cast concrete beams and columns with the precast concrete plank floors. So there's a number of different cases shown here, again, broken down into impacts by foundations, columns, and beams, walls, roofs, and floors. We achieved different levels of savings at each one of these cases here, starting at about 13% savings for the fly ash case, 14.2% savings for the changed over from site cast to precast, and then 32% savings when we swapped the concrete for a steel frame. So again, in that final case there, most of the savings came from swapping the site poured concrete for steel or precast concrete. And then some material substitutions, replacing metal panel and brick cladding with lower GWP materials such as stucco and fiber cement. And again, when you replace those materials, maybe the fiber cement and the stucco, they're going to have a lower, shorter lifespan than metal panel and brick cladding. But over the 60-year time frame, those should be evened out. You select the building lifespan so that you're getting several replacement periods. And it turned out for those two specific material types that was still going to be less GWP than what was included in the metal panel and the bricks. Okay, so how do you actually achieve those kind of things in the field or in practice? You know, you have to have a pretty well thought out workflow. And it really comes back to starting as early as possible. Start in the schematic design phase, keeping a record of the changes as you go and including the whole design team. So you've got to have structural engineers on board if you're trying to change, obviously, from site cast to precast or a different, you know, like a steel or even a wood frame building. That's got to be under discussions with the structural team very early on. The thing to avoid here, obviously, is coming in too late and you get through your schematic design and design development, and then you start doing your whole building LCA models when you've already got your construction documents done. At that point, you know, obviously it's far too late to make any substantive changes, and you may not be able to meet the 10% reduction that's required. A better approach here, this bottom approach, is that iterative workflow where you're working, the whole team is working together from the very beginning, proposing ideas, testing them out, going back to the drawing board, changing this or that, even maybe changing the design of the building to reduce the surface area. You know, those are changes that have to happen very early on. That top one is the one we'd like to try and avoid. So this was a nice chart I found. It was provided by the Embodied Carbon, the Carbon Leadership Forum, I'm sorry. You may find this helpful. You can download it from their website. Kind of establishing the key things to keep track of and accomplish at all these different design phases. So obviously the structure needs to come in very early, the early schematic design, the whole building design. Again, you know, massing, the massing needs to happen as early as possible. Optimizing the enclosure can come in a little bit later, maybe towards the end of the schematic design phase. And then when you get into the design development, you can start drilling down to these remaining, what they call hotspots, maybe specific materials, maybe specific assemblies that have high embodied carbon that you can design out or swap for different materials. Let's see, just checking the chat real quick. Path 2 is overall very similar to path 1. It's just an attempt to kind of reduce the workload a little bit. If you have a large building, complex building, and you feel that it's represented well by kind of taking just a slice out of the building, that's possible. So again, the reduction target is 10% of global warming potential as compared to the reference case. This is the example we're going to use as an in-class exercise on Thursday. So no, it says Wednesday there, but that's a mistake. It should be Thursday. The approach is a little simpler because there's just less takeoffs, there's less modeling involved. And as long as you are able to find a representative slice of the building, this is a valid path. The modeling requirements, as I mentioned, those are the same as path 1. You want to include, let's see, I think I've got a picture here, kind of a typical slice through the building. This is a look at what we'll be modeling on Thursday. If you are going to be doing this for compliance purposes under path 2, you'd want to make sure that the slice was complete. In this picture, there's no wall on the back side. You'd want to have a slice that goes clear through the building. So there'd be cladding on both sides, at the front and the back. you want to make sure you capture everything in the slice from all the way from the foundation up to the roof. I think that's all captured here. To omit, we can omit the same things as in path 1, plus now we allow this to take out the unattached parking garages. So that could be advantageous for some project teams. Using this approach, there is a more limited number of options available for reducing your embodied carbon. There's some things you're just not going to be able to do with this approach. For example, you can't play around with the building shape, trying to optimize the surface area or the layout of the surface area of the enclosure or the layout of the building. So it's also difficult to modify the structural spacing because it's supposed to represent one kind of bay. And if you're changing that size of the bay, you're not going to be, there's not a real way to capture that, the advantage of that doing this type of modeling, because it's always got to be one bay wide. You still can do some of these other ones though, the assembly substitutions. You can do structural changes like changing out a steel grid for a concrete grid. You can do window to wall area ratio changes. So there's still a decent number of options there. And of course, the material substitutions are still available. I think I'm going to probably skip through most of this. It's pretty much the same as path 1. Let's see my time here. I think we'll just skip the break too. Path 3 is kind of the black sheep. It's a bit of an outlier compared to the first 2 paths. It uses, I mentioned, this material selection calculator. And we can try and achieve an impact score of less than 1.65 if we've got a standard building, or less than 1.75 if we have a B3 small building. And again, this compliance path is limited to building projects that are using one dominant structural and enclosure type. It has to make up at least 60% of the building's structural volume or exterior surface area, respectively. And in addition, the project's assemblies and materials, they have to be well approximated, at least by the material selection. They have to be contained in the material selection calculator. So there's going to be some product types you won't be able to find in that. And in that case, it might be better to use a whole building LCA with a larger selection of products, or even something like, I think in Tally, in one click, you can build up your own results for a building material if you need to. Of course, this is, while it's the easiest path, it's also the most limited in terms of the number of options available to you. You can't really take advantage of any of these design solutions. The only thing you can really do using this path is to swap certain materials, one material out for another, and try and achieve kind of an optimization on the material front. Okay, modeling, again, there is no modeling requirements. We're using this selection calculator. However, it's important to keep in mind that if you do select this approach, one whole building LCA model is still due at the end of the CD phase. Unless your building is fitting under the B3 small buildings approach, then that requirement is omitted. So as early in the SD phase as possible, if you're going to use this approach, you want to start identifying the most common material types. Each of these 10 categories, there's 10 different categories built into the calculator. And you see those listed here. I'm sorry, the slide got a little rearranged here, but I think it's still legible. So there's cladding, low slope roofing, pitch roofing, columns and beams, which is this kind of the structure, exterior wall material, then a bunch of cavity, different insulation types for both the wall and the roof and then the foundation. So you get a chance to select materials from each of these different 10 categories. If there is a category that your building doesn't use, for example, let's say you don't have cavity insulation in your wall, you're using exterior insulation or board insulation, then that category is simply omitted. Yep. So step 2, you want to start entering these materials into the calculator. And as the design progresses, you want to start finding substitutions that you can make that drive your score down below 1.65 or 1.75 if you're a small building. So I threw in some of these charts. The group last time I presented this last December, and the group then found these charts to be really helpful. These are kind of like the background. This is what the material selection calculator is built from. So if you want to take a shortcut and find out, the quickest, rather than dropping, and playing around with the tool and experimenting with all the different options there, you can look at this chart and just figure out, well, this is the type of cladding, for example, that's going to be lowest impact, and just jump right to the solution in each of these different categories. So this is kind of helpful also to get a sense of, if you're doing a whole building LCA model, you can look back at these charts and get a quick sense of where those hot spots are, or what the worst materials are. For cladding here, we can see the metal panels are well above everything else in the field. Concrete block, concrete brick, and brick are also very high. And then we have a bunch at the bottom, towards the bottom, fiber cement, stucco, cedar vinyls, and wood. These are given just kind of group classifications. Those are those group numbers, 1, 2, 3, 4, 5. Those group numbers are what is used to calculate your impact score. So again, the total that you're trying to stay under is 1.65. So by and large, you want to stay in kind of groups 1 and group 2. You could have a few categories that are up in group 3 or 4, or maybe even 5, but that means that most of the other categories you're going to have to really keep at group 1 or group 2 at most. So that gives you kind of a sense of where you need to aim. This is low slope roofing. So the built up roof, the traditional modified bitumen roofing, hot rolled and stuff like that. Those are pretty high impact. Some of the newer single ply or different membrane products are going to have a much lower GWP than those traditional methods. So TPO membranes, EPD membranes, those are group 1. PVC membrane is a group 3. For a structure, here we can see this concrete, the site cast concrete has by far the greatest impact, embodied carbon. Precast is kind of a surprising reduction when I saw this at first, about half of the embodied carbon as site cast. Steel is another significant drop below even the precast concrete. And finally at the group and down in the group 1 is the wood, glulam, or all of the large timber and engineered wood would fit in group 1. So there's some exterior wall assemblies that are included as well, and these are representing just the structure. So the insulation, as I mentioned, that's if you have cavity insulation or exterior insulation, that's taken care of in the insulation categories. This is really more about the wood structure. If you're talking about, I'm sorry. the structure itself. If we're talking about a wood frame, it would include the sheathing, or a steel stud that includes the sheathing. Again, the site cast concrete is really high. There's some better options, CMUs and concrete tilt-ups. Drop that impact down a bit. Steel stud comes in much lower, and obviously, again, wood is the best from an embodied carbon standpoint. When we flip over to insulation, there's one insulation type that there's a outsized impact. This is the XPS. We're talking about board insulation now. XPS is blown with has been blown with a blowing agent that has very high GWP, and that's why you see that it's just head and shoulders above all the rest. EPS, mineral wool, polyiso, those are all fairly similar in performance in terms of GWP. Let's see, I think there's a question in the Q&A. So the question is, what is to prevent a design team from creating a base model that is intentionally 10% worse than their final design when materials such as metal panel and site cast concrete are known to have very high GWP? So the answer to that is that we don't have a good way to police that. It relies somewhat on, an honest design approach and an honest evaluation. We're just asking that people use kind of their basic or maybe industry standard. If you already feel like your standard approach is already superior to industry standards, you can fall back to what you feel is an industry standard to create that reference model. But again, we don't have a great way to police that type of thing. So we're relying on teams to be honest about that. And yeah. Thanks for that question, though. I think that's a valuable question. Cavity, going back to the insulation, the cavity insulation, again, you see this pattern similar to the board, the foam board insulation, where there's one product type that's very high above the others. And again, that's a foam product that has a blowing agent using HFCs. So all these other, there's some differences. Mineral wool bat definitely has higher GWP than fiberglass bat. But a lot of them are so minor compared to the closed cell spray foam that they're all categorized under group 1. We're going to talk in just a few minutes a bit more about the XPS and the closed cell spray polyurethane foam. So there may be questions on that, but hopefully they're answered in a few minutes. Like right now. Okay, so just a note on the blowing agents. You see here this chart, there's polyiso, spray polyurethane, and extruded polystyrene. So polyiso, there's right now, it's the 3rd generation blowing agent is pentane. The GWP on that is 7. So it's really not a very, it's not a number to be concerned about. There may be other chemicals used in polyiso that the project team wants to stay away from. But in terms of GWP, polyiso is not that concerning of a product. These other ones, spray polyurethane and extruded XPS, extruded polystyrene, it's typically going to be the blue insulation, blue foam. Those are where you see numbers up in the thousands. And that's coming from the HFC molecules that they're using for blowing agents. You can see those are, 1,400, 1,030 for the closed cell spray foam and the XPS. So that's why we want to try and stay away from those products. It's that particular molecule alone, which is pretty much accounting for all that embodied carbon in those products. Have been working recently to develop new blowing agents for both closed cell spray foam and XPS. So those are shown down here. They're HFO based, and they're very similar in performance to this the blowing agent used in polyiso, at least in terms of GWP. So unfortunately, the limitation or the availability of those products blown with HFOs is still pretty limited. Some states they're more available, others they're not really available. So these final couple slides here, I thought I would just provide some guidance on this issue. The XPS products with low GWP, there's a few of them here. Owens Corning makes Foamular NGX. DuPont makes what they're calling reduced GWP styrofoam. And Kingspan is making GreenGuard XPS LG. So all of those are the low GWP options. They're blown with the HFO blowing agents. And if you use those, then we can avoid those really super high GWP of the XPS, of the other XPS products. Similarly, in the closed cell spray foam world, there is a new blowing agent. It's called Solstice LBA. It has a global warming potential actually of just 1. So that would be equivalent to carbon dioxide. There's a few products that are available made with this blowing agent. Demilec makes a foam called Heatlock XT HFO. HFO again referring to the blowing agent. Lapola makes Foam Block 2000, and there are some more others that I did not list here, but those top 2 are the biggest ones. If you are able to find, these products, Foamular NGX or the reduced GWP styrofoam, or find a closed cell spray foam, the Heatlock or the Foam Lock products, then when you're using the either a whole building LCA model tool or the material selection calculator, we will allow you to substitute lower GWP foam products for those. But you have to make sure that you can actually, you have to make sure that they're specified and you can actually, they're available for purchase. My experience in Minnesota is that those products are really hard to find at this time. Some states have actually have banned HFCs in the production of the foams. And so the low GWP products, both spray foam and the XPS, they're going to be easier to find in those states. And I've included a link at the very bottom here. If you follow that link, it takes you to a map region by region that shows, which states have this ban, and you could find, more likely find these low GWP products in those states if they're willing to ship. Okay. So how to achieve compliance with the Path 3 material level LCA approach. Going back to these 2 examples, the Wells Fargo office building. So this is a look at the material selection calculator. Just kind of a screenshot of the tab, of the Excel tab. And you can see the categories on the left-hand side. Then in the yellow box, these are where you make kind of the drop-down selections. And then it's showing you in the blue column what the impact score is. So if you remember, this building had some pretty high embodied carbon construction types, including metal panel cladding, modified bitumen roofing. That was a concrete site cast. So you're seeing a lot of 5s pop up in the impact category. They used XPS for the board and the board insulation in the wall and the roof and below grade. So This number, the impact score is quite high, 4.25. And when you get a score above 1.65, the little cell turns red and it says you failed that. So if we just go back and try some of the same strategies that we used in the whole building LCA model, we find that we can actually pass with using this approach. So we exchanged the metal cladding for fiber cement. We changed the roofing membrane to EPDM. We changed the site cast concrete structure to precast. And we swapped out some of the board insulation from XPS to various types of other foams, EPS and polyiso for the roof. And you see here, doing those, just making those material substitutions, we can get our impact score down to 1.63, and the cell at the bottom turns green and we get a pass. So at that case, if you had a small building, you'd be done. If you were doing a regular B3 project, this would be good enough to show compliance with the requirement, but then you'd also have to upload a whole building LCA model based on their final set of CVs. Okay, so that is the end of the presentation that I have prepared. So we've got about 20 minutes left for Q&A. If there's anybody wants to go back to different slides and discuss, open up a discussion about stuff, you can try and do that. Looking at the Q&A, I don't see anything in the chat or the Q&A at this point, but feel free to type away. All right, well, I'm not seeing anything come in. I'll send just a reminder for Thursday. Let's see, make sure to have the Athena software loaded. You want to stay away from the eco calculator. That's another free version of software that people sometimes download accidentally. What we're going to be using on Thursday is the environmental impact estimator. So make sure that that is downloaded and installed. Let's see, there's a question just popped up. Advice on how to get into Athena quickly. No, I think overall Athena is has one of the fastest learning curves. It doesn't take too much to just start throwing things into the tree structure. You don't have to have a finished building model. You don't have to do anything more than just test out a simple wall assembly, in fact. So if you just want to try some different wall assemblies, that's something you can try, like a concrete block wall versus a stud wall. And that'll give you some practice entering different assembly types. You'll see that Athena has a lot of, what's nice about Athena, it's got a lot of built-in assemblies. So if you want to enter a stud wall, you can just select a stud wall and say, I want a 2x6 or a 2x4, and I want to use this type of sheathing and this type of insulation, and it kind of plugs it all in for you. So some of those features are really nice in Athena. And I might suggest that as just a good starting point, just to model some simple assemblies, get familiar with the software that way. We're not going to be recording the Thursday session because it's a setup as more of as a regular Zoom meeting. There's going to be long periods where you all are going to be working on your own, and I'm going to be checking in on you to see, if you got any questions or how the progress is coming. So we're not going to be recording that session, unfortunately. Yeah, there's another note here in the chat about Athena for Mac users. I think you have to, I think using, well, that might be new. What I'm reading here, thank you, Hans Christian. What I'm reading there is it might be new and new news to me. If you do have issues with Mac, you can email us and we may be able to help you through that. We have some Athena users that have Macs here at the CSBR. So if you do have some issues with that, send me an email. We may be able to help you work through that. Okay, I think we're going to wrap up. This will be the official ending of the webinar. I will stay online for a few more minutes if anyone wants to stay in chat or ask some more questions. I'll be around, but thanks for your attendance, and hope to see many of you back on Thursday.